Hi, I'm Ron Daniels, and I'm the Coordinator of Science Entrepreneurship at Wilfrid Laurier University. I run the Science Maker Lab. One of the main things that we do here in the lab is that we teach SolidWorks so that people can design things to make on the 3D printer, the laser cutter, and in the Maker Lab itself. Today we're going to cover the very early stages of creating a drawing. We teach this lesson based on the assumption that the student has zero background in technical design or drawing. This is generally their very first CAD lesson. We want to ensure success, so we go slowly and thoroughly at the start, and then speed things up as the student has spent some time with the techniques and jargon associated with CAD and technical drawing. We'd rather spend a little more time with you up front than cut this process short, send you on your way, and then have you stuck and frustrated. You've now learned Silly Science Maker Lab mantra number 1. Slower is faster. Welcome to our world, and we hope you enjoy geeking out with us. In reality, the first CAD lesson is not actually going to use the computer-aided design, otherwise known as CAD, software. Before we open up the CAD and start to draw something, what we need to do is figure out what we want to draw. For the purposes of this lesson, we're going to create a little sign and a base that we call the tombstone, because it kind of looks like one. We found that this simple project covers all the basic techniques and concepts needed to get you to the point where you have the CAD skills to convert your ideas into CAD models with little or no intervention required by us. We're still there for questions or to help you get unstuck, but for most student designs that we've seen, you shouldn't run into too much that we haven't covered in this lesson. If you do run into a challenge that requires techniques not covered in this introductory project, you can try to teach yourself, learning from a huge library of YouTube videos of variable quality, or you can come back in for one of our advanced CAD lessons. Well, I guess it's time to get started. It's very hard to read someone's mind to see what they're envisioning, so even in today's high-tech world, it's really helpful to start out by clearly communicating what you want to make. To do this, we're going to need a basic sketch and we're going to need some dimensions. In the old days, like when I was in high school, the way to make a technical sketch would be to do a 3-view drawing. For our little tombstone, we would draw a front view with the outer ridge and the name Tom E. Stone. We need to do a side view. There would be a hidden line here to show that the face is recessed, and then you'd have a top view. And all of these would be projected from the other views. Right. So it works, it's good for dimensioning, but it's not really realistic looking at all, and it doesn't make sense to you if you're not a trained draftsperson. So we don't use 3 views. We do our dimensioning and planning drawing in such a way that it's much more closely aligned to what we're actually going to draw within the CAD. So instead of doing a 3 view, we're going to do it in an oblique view. We're also going to do it in what's called an exploded view of the assembly. We'll start off with the front of the top piece just like we did for the 3 view. It's going to have a tongue down here because it needs a tongue to plug into the base for the parts to fit together nicely. We'll have our little outline ridge here and our lettering, Tom E. Stone. Instead of projecting the view of a different side to show the depth, we're going to extend this project back on about a 30-degree angle with all the lines leading to just one side. Then it starts to look a little bit 3D. It's not a perfect 3D drawing, but it's one that shows us that the object has depth and it gives us access to all the different sides, and we can put dimensions on those sides. Then we'll draw our base below it. It will have to have a groove where the tongue will go, because this is a tongue and groove assembly. It can also be called tab and slot. The base has some thickness to it. So once we get this base drawn, we can start to put some dimensions on it. The width dimension for this base is going to be 100 millimeters. We know that 100 millimeters fits on our 3D printer, so if we decide to 3D print this rather than laser cut it, it will actually work on the machine that we have. We'll stop for a moment and we'll talk about the lines here for a little bit. These lines here, the leader lines, lead to the corners or vertices that you're measuring between. The dimension line, which is the arrow here with the gap in the middle for the numbers, runs the length of whatever you're measuring, and it always runs parallel to the vector that you're measuring along. You put your dimension in the gap in the middle. You can see the value of 100 millimeters written there, or as it looks in my handwriting, 100 millimeters. So that's how we put a dimension on a rectangular drawing. We'll add the other dimensions so that every size or length that needs to be defined is given a value. On the thickness, there's not a lot of room to write, so it's acceptable to put the arrow on the inside and then put the 15 millimeter value on the outside. The tongue is going to have a depth to it, but that depth, if we want it to sit flush with the bottom of the base, is going to have to be the same as the thickness of the base. Since we're working with 4.7 millimeter plywood and we want 2 layers because we know that gives us enough thickness to get a fairly stable joint, plus it looks nice. So we'll put a dimension on this height and we'll go 4.7 times 2, which is 9.4 millimeters. Right, so this means that the tongue is also going to have to be 9.4 millimeters. The thickness of the tongue front to back is going to be 1 layer, so we really don't need to put a dimension there because we know it has to be 4.7. Now we'll set the height of the upright to 60 millimeters. We're still missing one measurement, and that measurement would be the width of this outer lip. So, oops, that's not 15, that's 4.7 times 3, which is 14.1. Now back to the lip. The depth is 4.7 because it's just 1 layer of wood. And the width here will be 5. That's a good number. It's arbitrary. We could go with 5, we could go with 6, we could go with 7, we could go with 10, whatever. But we know that 5 tends to look pretty good. This bevel part here, we're going to deal with that later. The width of the tongue now needs to be decided. We'll take a little theory break and we'll talk about the width of this particular feature on this part. The purpose of the tongue is to connect the upright to the base. If we were to build this part and then grab the upright from the top and try and twist it like this, we're effectively setting up a vertical axis in the middle of the upright. The furthest out that we can push on this would be this edge and this outer edge. With an overall length of 80 millimeters, what this means is that the maximum lever length that we can achieve over this axis is 40 millimeters. We've got our pivot point here, and we've got an 80 millimeter length, and that's half of that, so that's 40 millimeters. Right. So we've got F here. Force F pushing up on this end, and on the other end, we have another force F pushing that end down. But we don't have to do the calculations on both sides, so we'll just worry about the one side. The length of that side is 40 millimeters. As we'll go into in more detail in the gears CAD lesson later on, the linear force on the end of the lever sets up a rotational force around this axis. The value of that force is going to be F times 40 millimeters. As this force travels back along the tongue to the part of the slot that's going to try to resist moving under this force, we can see that all of the force is going to wind up concentrated at the corner at the end of the groove. If rotation could happen, this would be the part of the groove that would move the furthest for a given rotation of the axis. So it's going to be the first point to feel the load because until it actually yields, none of the other stuff along here would even get to feel any of the load. Because of this fact, we can simplify to assume that all of the force from this rotational movement is going to be carried by this one little corner. So if we make this tab and slot assembly, say 30 millimeters in total width, that's going to be 15 on each side of the axis of rotation. To calculate the force at that point, we would have to convert between torque and linear force with our old high school leverage calculations. So rotational force at the axis is F times 40. But then to turn that back into a linear force here, we now have the original 40 times 40 over 15. 40 over 15 is 2 2/3 or 2.67, so our 40 units of input force is going to be felt by the tab as 106.67 units of force. If we were to make the length of the tab and slot both 70 instead of 13, then the effective lever arm would be 35 millimeters. Now we'd be looking at 40 times 40 over 35 to figure out the amount of force felt by the corner of the tab and slot. 40 over 35 is 1.142. Times 40, that's 45.68. Compared to the force if we used a 30 millimeter tongue, this is less by a factor of 2.335 times. So ideally, the tongue length would be maximized to be the exact same width of the upright, right? Well, from a strength point of view, yes. If you make it 80, it's going to be nice and strong, but that's not going to look very good because there's going to be a little bit of visible slot here on the outside because we actually have to cut the slot a little tiny bit bigger and wider than the actual tongue, or the tongue won't be able to go into it. But generally, bigger is better, so if we make it 60 or 75 or 70, we're going to have a good outcome from both the strength and an aesthetics point of view. We can choose any of these happily. Now we have our little roughed out drawing, and this is kind of what the parts are going to look like in the CAD because the CAD works with three-dimensional drawings. We've got all our dimensions that we need. It's not a pretty drawing, it's not proportional, and it's not to scale. But it shows the basic shapes, it shows the relative locations of the features, and it denotes how big they're supposed to be. All of these things come into play when we start drawing in the CAD. The fact that it's not to scale doesn't matter because we use SolidWorks, and SolidWorks has driving dimensions, so the CAD will allow us to force parts to go to whatever dimensions we put in. Think of it like active and passive. A passive dimension, driven in SolidWorks, tells you how big something is. An active dimension, called driving in SolidWorks, can be edited to force the part to change to a size or location to match the dimension that the user types in. So we're actually going to get pretty good use out of this drawing that we put on our whiteboard, or our paper, or our napkin, or whatever, and it'll help us progress in the next step of our drawing. And that looks like a good spot to stop for Lesson 1, Part A. Thank you.